Check it out now, y'all.
nanoHUB-U, online instruction.
Hi, and welcome back to Lecture 2, Week 2 of Dynamic Atomic Force Microscopy Methods. In the last class, we had been talking about how the amplitude and phase response of a point mass oscillator model for dynamic atomic force microscopy, how it's influenced by the interaction forces between the tip and the sample. And we talked about the fact that there are two main effects that happen. The first is the fact that if this was the typical resonance curve, as you come close to the sample, this resonance curve starts shifting due to attractive force gradients. It moves to lower frequencies and then shifts to higher frequencies due to repulsive force gradients. In addition, as you approach the sample, the resonance curve can actually broaden due to increased dissipation between the tip and the sample. And this is shown in this three-dimensional graph here, which we covered in the last class, which shows that as you approach the sample, how this resonance peak first shifts one way and the other, and how it becomes broader. The other thing we talked about was the fact that the phase response, which is the phase lag, again, as a function of the drive frequency or excitation frequency, it undergoes an interesting transition as you approach the sample, in that the location or the frequency at which you encounter the 90 degrees phase lag changes according to how far you're from the sample and depending on the interaction forces between the tip and the sample. Now, based on this understanding, we had talked about if one were to try and approach the sample using dynamic atomic force microscopy, you might want to do it using three different ways. The first would be you would keep the drive frequency fixed and then approach the sample by changing Z. And in doing so, one would observe a change in oscillation amplitude and a change in oscillation phase. What we really stressed last time was that when you do such an experiment, the amplitude decrease that occurs happens due to a combination of two effects. One effect is this resonance peak actually shifts from underneath the fixed drive frequency you're at. As a result, you're no longer at the peak, and so the amplitude tends to drop. But also because even if the resonance frequency didn't shift, the decreased Q factor would reduce the amplitude. So it's a combination of two effects that conspire to reduce the oscillation amplitude. So one could keep the excitation frequency fixed and approach the sample and monitor how the amplitude changes with distance, or and additionally how the phase changes with distance. Or one could approach it hypothetically by tracking the resonance frequency, and one would do that by changing the drive frequency so that the phase lag is always at 90 degrees. If one were to do that, then as you approach the sample, you would find the amplitude just keeps decreasing, and the phase remains constant because you're now maintaining the phase lag constant. But this time, the decrease in amplitude would be only due to dissipative effects, since the drive frequency keeps shifting so that you're always at resonance. A third technique of approaching the sample we discussed is trying to increase the excitation amplitude so that the oscillation amplitude of the tip remains constant as you approach the sample. And in this particular case, in this last case, the amplitude would remain constant, the phase would remain constant, but the drive frequency, or the frequency shift, would change as you approach the sample, and the excitation, the drive excitation, would change to maintain a constant amplitude as you approach the sample. So there are three different hypothetical ways of approaching the sample we talked about last time. And really what we'll do today is to see how that basic understanding forms the basis of common scanning methods in dynamic atomic force microscopy. But before we move ahead, it's important to take a little detour and talk a little bit about how one would actually measure the amplitude and phase and track the frequency shifts and track the phase, for example. A key instrument or a key component of an atomic force microscope these days is the lock-in amplifier. And the goal of the lock-in amplifier in an AFM is to extract the amplitude and phase of the signal that's coming out of the photodiode, which is detecting the motion of the cantilever. So why one uses a lock-in amplifier is basically because often the signals coming out of the photodiode might be noisy. There are a number of noise sources. You could have laser shot noise. You could have harmonics, noise, 60 hertz signals, a lot of things that can contaminate the signal that you observe from the photodiode. But what we want to do in the photodiode is, in the middle of all this noise, we want to isolate the motion of the cantilever, which occurs at the drive frequency. Remember, if we choose to drive the cantilever at a frequency omega, it's going to respond at that frequency. And so that's where a lock-in amplifier really helps. Now, what I've tried to sketch out here is briefly what the conceptual idea is of how a lock-in amplifier works. So let's say you're interested in extracting from a tip displacement signal that comes out of the photodiode. Let's call it QT. We're interested in extracting out a component A sine omega t minus phi. We want to find out what A is and what phi is, while we have other harmonics and other noise that might be present. Well, one way to do it would be to take the signal and multiply it by sine omega t. And when one multiplies this through by sine omega t, one would see that when the sine omega t multiplies with the sine omega t minus phi term, you actually get a DC term, which is going to be a cosine phi divided by 2. And the other terms are all going to be at different frequencies, are going to have non-zero frequency content. In the same way, one could multiply the same signal qt by cosine omega t, where omega is the frequency at which you're interested in finding the amplitude and phase at. And when you do that, you get the same thing. Now, remember, what we're trying to get out of the signal is A and phi. And therefore, if I multiply the signal by sine omega t and by cosine omega t, if I look at the DC component of the signal, I'm basically getting A cosine phi and A sine phi divided by 2. And this is the basic idea of a lock-in amplifier. And so what really happens is you take the signal that you multiply by sine omega t and try to filter out all these other noise components to extract out the DC component of the signal. That can be done by integrating, as I've shown, the product over a long enough time range, which is called a lock-in time constant, T-lock. And when one does that, you can look in the appendix for some details. Basically, one filters out all the harmonics, all the noise, and you're basically left with A sine phi over 2 or A cosine phi over 2. So once you have these two signals, they're called X and Y components of the lock-in amplifier output. You can get the actual amplitude by multiplying by 2 and squaring and adding X lock squared and Y lock squared. And the phase is simply then the arctangent of Y lock divided by X lock. Now, an important feature of a lock-in amplifier is this lock-in time constant. The longer the lock-in time constant is, the more effectively it throws out noise and frequencies. The shorter the lock-in time constant is, the faster it responds, but it's not as effective at rejecting noise in this product signal. Sometimes the inverse of the lock-in time constant is also used, and that's F sub lock, and that's the cutoff frequency, basically. And that tells you, when you look at the product of Q of t with sine omega t or cosine omega t, what are the frequencies that you're filtering out. So basically, we have what's called a low-pass filter. We're trying to filter out the noise and just trying to extract the DC component of the signal. So that's the essence of a lock-in amplifier. And so now we have zoomed out and got a flow chart of how a lock-in amplifier works on AFM data. And what one sees here in the flow chart is, as the cantilever oscillates, the reflected spot on the photodiode moves up and down, causing an oscillating signal with noise added to come out. And one goes through this flow chart and one can see how you would generate a signal, omega, at frequency omega, that would then drive the cantilever, let's say sine omega t. And you use the same signal that's driving the cantilever as a reference signal, and you would multiply the measured output from the photodiode by sine omega t, then you would take the same reference signal sine omega t shifted by phase and by 90 degrees and produce a cosine omega t signal. Go ahead and multiply that with the output of the photodiode and make it go through this low-pass filter or this integration module where the lock-in time constant comes in. And what it would spit out would be this x lock and y lock, which are proportional to amplitude times cosine phi and amplitude times sine phi. And so that's how, in near real time, one would be able to find out what the amplitude and phase of the oscillating output is. So on the top right, I've shown an example of how the time-varying displacement of the probe might change as you approach the sample. You see there's this high-frequency oscillation of the cantilever is oscillating at a high frequency. When it approaches the sample, the amplitude decreases, and we have discussed why that would happen already. The amplitude decreases, and really one can think about a lock-in amplifier as being a way to extract how this slow timescale variation of amplitude and phase is happening. What I mean to say is, if you think about how the cantilever is moving, the AFM tip is moving, it's got this really high frequency component, but then its envelope, or the amplitude and phase of it, are changing much slowly compared to the high frequency oscillations of the probe tip. And so what a lock-in amplifier really does is it's taking you from this high frequency oscillation to the overall envelope of response, both in amplitude and phase. And so we can think about it as a way to observe the slow timescale dynamics of the oscillating probe. Now comes the second part of the question. How would we track the phase and frequency of the oscillation as you approach the sample? And for this, one would use a phase-locked loop. Many AFM systems actually come equipped with phase-locked loops. And here I've shown a flowchart that essentially describes the key component of a phase-locked loop. What would happen in a phase-locked loop is we would go through the same lock-in amplifier that I showed you before that would spit out the amplitude and phase of response relative to a reference signal, which is the signal exciting the cantilever. However, when we're using a phase-locked loop, what we typically want to do is to change the drive frequency omega so that the response always remains at a fixed value of phase, typically 90 degrees. So the output of the phase of the lock-in amplifier would then be compared against a set point phase, or phase that you want to maintain constant, and any difference between the desired phase and the actual phase is used as a signal with a gain on it, with an element that amplifies the signal, to change the drive frequency omega so as to drive the difference between the measured phase and the desired set point phase to zero. So in this way, what happens is, in a dynamic feedback loop, one is able to change the drive frequency to basically track the natural frequency of the probe. And so now let's go on to actually talking about how these different imaging modes work. The first major imaging mode that we'll talk about is what's called amplitude modulated AFM. This is called the tapping mode AFM. Now, in amplitude modulated AFM, it's also called AM-AFM. What one does is one uses a fixed excitation frequency, F or omega, and you drive the cantilever with some initial amplitude we call A free, and phi free is the phase. When it approaches the sample, and as we've talked about, the amplitude and phase are going to change because of these intermolecular forces between the tip and the sample. And let's say they change to a value A and phi. Now what happens is one would scan over the sample, and the controller tries to change the Z separation, which one can do by either changing the sample position or moving the base of the cantilever up and down. So one would change that. In this case, I've shown it by moving the base of the cantilever up and down. One would change the Z in order to keep the amplitude constant at certain value A. So as a result, you can see as the cantilever is scanning over the sample, oscillating like so, when it hits an object, its amplitude would tend to decrease because there's less room to vibrate. But since we're measuring the amplitude and we find that the amplitude is less than the set point amplitude, the controller would adjust itself, move the base of the cantilever up in order to get the same vibration amplitude, and then you would keep scanning over the substrate. So in this simple sketch, the red curve is the curve that you would move up and down along in order to maintain a constant oscillation amplitude as you interact with the sample. And that red curve is effectively rendered as a topography of the sample. Now, when one looks over an object that one is scanning, like I've shown in the middle here, and let's say this object has slightly different properties compared to the rest of the sample. Perhaps it's stickier, perhaps it's softer or squishier. What would happen is the amplitude remains constant, but the phase might change from different parts of the sample. Because remember, in amplitude modulated AFM, all we're doing is controlling the amplitude as we scan over the nanoscale objects. But we let the phase evolve depending on whatever tip-sample interaction forces might be encountered by the tip. So in this case, topography is rendered along the red curve, and phase would be a separate channel that will just tell us something about the material properties of the sample. So here I demonstrate a few examples taken from the literature on tapping mode atomic force microscopy images. On the top left is an example of, on the left you see a topography image of wood pulp, and this is an image that's come out of advanced surface microscopy. And on the right side, corresponding to that image, is a phase contrast image. So one can see that we get very complementary information. On one side, one sees the topography of wood pulp. On the other side, one sees the composition, the local material property contrast. And in fact, by looking at the sample, one can tell the difference between the cellulose fibrils in the wood pulp and the lignin patches that are also spread all over the sample. Another example on the top right is a polybutadiene polystyrene blend. Again, this is taken from the literature. And polymer blends are a very good example where phase contrast, tells us a lot of interesting information. And we'll talk about phase contrast a little later. But on the left is the topography image. So again, this is, as you scan over the sample line by line, the question is how much do you move the base of the cantilever up and down by in order to maintain a constant amplitude? That's the topography on the left. And the topography does not really show us a big contrast between different regions of this two-blend polymer system. On the other hand, when one looks at the phase contrast on the right-hand side, that does change as you go over different parts of the sample. On the bottom left, again, is another example of a topography phase contrast image of a cadmium, zinc, selenium semiconductor system that again shows that topography tells us the roughness of the object, but the phase tells us more information, different information, more about the differences in forces between the tip and the sample as you scan over the sample. On the bottom right is a biological example. This is an example of two bacteria that are actually coated by a polymer sheath. On the left is a topography image, and on the right is actually a phase contrast image that's able to point out that while the topography is relatively smooth, the underlying properties and the forces encountered by the tip change from point to point of the sample, giving us an interesting insight into what lies underneath the surface. And so here I show an overall flowchart for tapping mode atomic force microscopy. So based on what we have discussed, we have an AFM cantilever, and we drive it with excitation frequency omega, preferably close to the drive frequency omega naught, and we move the Z piezo, or the sample position, up and down in order to keep amplitude constant, and all the time we allow the phase, which is the output of the lock-in amplifier, to change from point to point on the sample. Finally, we're going to talk a little bit about frequency modulated AFM. In frequency modulated AFM, this is the other very commonly used mode of atomic force microscopy. Frequency modulated AFM works on an interesting concept of multiple feedback loops. So here what happens is, as you're interacting with the sample and scanning over the sample, the drive frequency F is no longer, or omega is no longer fixed, but rather it always changes to track f0 prime or omega naught prime, which is the altered frequency due to the tip sample interactions. And this happens by using a phase lock loop. And you can see the phase lock loop again appears in the flow chart here. So the output of the photodiode then spits out the amplitude and phase. The phase lock loop then changes the drive frequency or excitation frequency to keep the phase lag equal to 90 degrees. A second feedback loop that is embedded in FM-AFM is to change the excitation amplitude so as to keep the tip oscillation amplitude constant. So as it scans over a sample, the tip oscillation amplitude is held constant. Its phase is held constant, but both of these things are accomplished by changing the excitation frequency so it matches the natural frequency of the probe, the modified effective natural frequency of the probe, and by changing the excitation amplitude to keep the amplitude constant. And so one then changes the Z in order to keep the frequency shift constant. Again, the details are provided in the appendix, but the Z then changes up and down to keep the frequency shift constant. And remember, the frequency shift is related to the gradient of the tip sample interaction forces. And so when one takes an image with frequency modulated AFM, it's basically a level set of heights above the sample where the gradient of the tip sample interaction forces is constant. On the other hand, in tapping mode AFM that we have studied before, all that you maintain constant is the tip oscillation amplitude. And that changes due to both dissipative and conservative interactions between the tip and the sample. So tapping mode image is a level set of constant amplitude. It's not fundamentally a level set of constant force gradients or constant dissipation. So I want to highlight two classic works from the literature on frequency modulated atomic force microscopy. The first one on the top left was the first reconstruction of the silicon 111 surface using frequency modulation AFM with atomic resolution, which meant the lateral resolution had to be less than 6 angstroms in this study. This was a particularly important study that came out in Science because it was one of the most important surfaces whose atomic structure had been resolved using STM before. And before this particular paper came along, there was always a doubt whether dynamic AFM could be able to achieve this atomic resolution required to reveal the structure of this silicon 111 surface. On the bottom right, I show an example of a metal alloy. This is again a recent paper using dynamic frequency modulation AFM, and you can see atomic resolution images of silicon and tin atoms, amongst others, on the surface. And in this particular example, actually the work went down further to use FM-AFM to actually detect the differences in chemical forces between the tip and the sample, between these different atoms that are on the substrate. So with that, I'd like to conclude, and we will continue this discussion in the next lecture.